Welcome to Maths with EJD. In this fourth video on vectors, I'll be talking about application of vectors in geometry and physics. Come along in this interesting journey. Let's start with geometry. Applications, applications of vectors in geometry. Of course, geo is something like earth, or you can look at it like a flat surface. The metry is measurement. So we're talking about all kind of measurement that you can take, like talking about area, perimeter, and things like that. So this is the kind of thing that you'll be coming across right here. So application of vectors in geometry. So let's start with vector addition. Let's see how vector addition plays part in this place. Vector addition. Okay. Um, consider a triangle with vertices ABC, vertices A, B, and C. Vertices A, B, and C. A, B, and C. So vertices are like edges. Then the vector representing the side BC, the side BC is actually BC, which is equal to C minus B. In another form, you can actually say it's like OC minus OB. That means that is with a reference to the origin. So it's more like I think I should be able to do a kind of representation of this. Imagine that you have, okay, I guess I need a bright color here. Okay, let me do green. So you have something like this. So this is from the origin, you have vector, you have vector C, and then from the same origin, you have vector B. Okay, so if you want to get this line between B and C now, so that'll be OC minus OB. OC minus OB actually gives you the distance between it gives you the distance BC. So if you're looking for CB, that'll be so you go ahead. So CB will be OB minus OC. So it's a very simple thing. So it's like you're taking, I think it has a name now. You're taking the vector with respect to the origin. So that's the kind of thing that is happening when we come into geometry. Of course, I'm going to come up with an application pretty soon so you can understand better. Okay. So similarly, the vector representing the vector representing the side AB, of course, would be the vector AB, which is equal to B minus A. So if you like, you cannot, like I said, you can call it OC minus, that's OB minus OA. OB minus OA. So with the idea that you are taking the two vectors yeah, with reference to the origin 0. Okay. All right. So how does this play out actually? So in geometry, vector vector addition can be used to find the resultant. We talk about the resultant of vectors. It can be used to find the resultant vector, when adding two sides of a triangle or other polygons So vector addition can help us to find resultant vectors. So for example, the diagonal of a parallelogram of a parallelogram. Parallelogram formed by vectors A and B is given by A plus B. So a representation of that would be something like this. A parallelogram simply means the two sides are parallel, like they have two opposite sides parallel. So you have something like this. So this is parallel to this, and then you have this parallel to this also. And the beautiful thing is that the opposite sides are equal. So let's say this is side A, and this is side B. Of course, that means this is also side A, this is also side A, and this is side B. So the diagonal of this parallelogram now, okay, can actually be, so that is what you have as A plus B, like that. So that's the idea. So vector addition can actually help you to find the resultant of two vectors. So it's more like resolving the vector. So that's like the using the components. No, I mean it's a different idea actually. So I think the nice concept is the idea of resultant. So let's take a practical example of this and see how that looks like. So let's say that we have suppose you have a quadrilateral. A quadrilateral is a four-sided polygon, just like a triangle is a three-sided polygon. So suppose you have a quadrilateral A, B, C, D with position vectors A, that is 1, 2, A, that's 1, 2, that's, you have just the ij. So these are two-dimensional now. So you have 1, 2 in the ij components, in the ij directions. So you have B, which is 4, 3. You have C, which is 6, 5. And you have D, which is 3, 4, like that. Okay. So to find the diagonal vector AC, find the diagonal vector AC, you add vectors AB and BC. So okay, let's even try and picture the diagonal, the quadrilateral. Let's say it's something like this. Okay, let's use like, okay, it can be a rectangle. Can it be a rhombus? I'm not sure. So okay, let's even use a rectangle. I mean, let's just assume. So this is A with 1, 2. This is B. So this is C. This is D. Of course, they are all vectors. So with all their respective components, 1, 2, and all the rest. So we need to find the diagonal. We need to find the diagonal AC. This is the diagonal AC. This is what we are looking for now. So, and that is the addition. Of course, to get the diagonal AC, as you can see, AC, to move from A to C is actually like moving from A to B first. That's AB plus then moving to from B to C, BC. That's simply the idea. And then, of course, to do that, right, we have to break it down the way I explained earlier. So that's AC is equal to, for AB is B minus A, as you know already. So that first part plus BC is C minus B. That's what I explained, what I did in the explanation. So it means that AC itself is actually, so B minus A, we know B is 4, 3. So that is 4, 3. Then A is 1, 2. So 4 minus 3, 4 minus 1, 3 minus 2. that is this part now, plus C minus B. C is 6, 5, 4, 3. So 6, 5, that's C. Then B is 4, 3, that's minus 4, minus 3. So that at the end of the day, you have AC to be 4 minus 3. So that's 4 minus 3. That is 3. 3 minus 2, that's 1. Plus 6 minus 4, that's 2. 5 minus 3 is also 2. So that AC itself is actually, so the line segment AC, which is the diagonal, is actually 3 plus 2, 5, 1 plus 2, 3. And that's it. So AC, the line AC can actually be said to be 5i plus 3j, like that. So that's a very good example of vector addition for resultant of vectors. So you can see AC is actually the resultant of AB and AC. And it's better to do the, I think it's, yeah, this is the idea of position vector. That is taking that with reference to the origin position vector. That's what I was looking for. Okay, so that's one application in geometry. Let's check out another application under geometry apart from vector addition. So let's move on to, still under geometry, let's look at vector projections. Okay, vector projections. So let's talk about vector projections. That's the second thing, the second application under geometry, vector projections. Okay. So for vector projections now, if we are given two vectors, so given two vectors A and B, two vectors A and B, the projection of vector A on vector B is given by so what you can call proj. So we are projecting A on B. So that is vector A on vector B. So this is the notation. So you're projecting A on B. That is what it looks like. And that is actually equal to vector A dot vector B. So the dot product of A and B divided by the magnitude of B, the square of the magnitude, multiplied by the vector B itself. That's the projection of A on B. So what that simply means is that, so it means if you're projecting B on A, so you're going to have, so okay, to projecting B on A, let me just do that. Projecting B on A, vector B on A, would give us some, so we have the other side, that's projecting, since we are projecting B on A now, so that's B on A, and that is equal to, again, if you like, of course, the dot product is commutative, so you have B dot A divided by, since you're projecting on A now, so magnitude of A all squared multiplied by the vector A itself. So that is what that looks like. And what is the application of this particular kind of thing? So the application is such that vector projections are useful. They are useful in calculating distances, between points and lines, in geometry. For instance, the shortest distance from a point, to a line, can be found using projection of the position vector using the projection of the position vector of the point onto the direction vector of the line. This is like plenty English. Let's take something practical. To clear that out. Okay. So talking about projection of vectors now. Okay, we have a very simple example which we can quickly deal with. Okay. So vector projections, right? An actual example. Given vectors A, which is 3, 4, and B, which is 1, 2, and B, which is 1, 2, the projection of A onto B is proj. So we are projecting A on B. So that's A on B like this, and that is equal to A dot B divided by the magnitude of B squared multiplied by B itself. And how does that go? So we have so that simply means we have A is 3, 4 dot B, which is 1, 2 dot B, which is 1, 2, divided by the magnitude of B itself. That is, so the magnitude of B would be, okay, let me just put the notation first. So that's the magnitude of B, which is 1, 2, the magnitude of that raised power 2, and then all of that multiplied by B, which is still 1, 2. So we just have to resolve all this now. So the unit vector of A and B will just be 3. That will be 3 times 1. It's just I and ij and j. So 3 times 1 plus 4 times 2 up there divided by the magnitude is simply the square root of 1 squared plus 2 squared, and that is multiplied by the normal vector 1, 2. So 3 times 1 is 3, 4 times 2 is 8 divided by square root of 1. I mean, 1 squared is 1, 2 squared is 4 rather, 4, and all that is multiplied by the vector B itself. So 3 times 8, 3 plus 8 is 11, and so that's 11 over square root of 5 multiplied by 1, 2. Okay, so we have something like this. Okay, sorry. This magnitude now is squared, sorry. So so we have the square of this. Sorry, the square of this. And of course, the square of this. So the square of a square root is actually the number under the square roots. So that's 11 over 5 into 1, 2. So if you do that, that means you have, okay. You can leave it like this, right? But you can put it inside 11 over 5 times 1. That's 11 over 5. 11 over 5 over 5 times 2, that's 22 over 5. So we're talking about the projection of A on B. So that's proj A on B, actually. So, let me write it better. So, okay. So the projection of A on B, that is what it gives us. Of course, it can actually be 2.2. 11 over 5 is 2.2. 22 over 5 is actually 4.4. So that's the projection of A on B. Of course, this is also a vector. So you can write that 2.2i plus 4.4j. You can actually do it that way. So that's the idea of projection. And just like we've seen already, you can use it to calculate the shortest distance between a point and a line. So of course, if you want to do the projection of B on A, you just reverse things. So you just have B dot A over A magnitude of A squared times A. So that goes. So let's talk about the third application of vectors in geometry, and that is talking about cross product in geometry. Cross product has a geometrical meaning. We saw cross product under vector operations. So cross products in geometry. Cross product in geometry. So the area of a parallelogram, formed by two vectors, A and B, is given by the magnitude, of their cross product, the magnitude of their cross product. And that is simply the magnitude of A cross B, like this. So that is, so the magnitude of A cross B, if A and B form a parallelogram, the area of the parallelogram is actually the magnitude of the cross product of the two vectors. So as for application, we say the cross product is used to determine the area of parallelograms. We can actually talk about parallelograms and triangles, parallelograms and triangles as well as to find the normal vector to a plane, in 3D space. So if you want to explore this one on your own, just check it out in some textbooks or online. Okay. So having talked about that, let's take an example that drives the point home. Okay, so example, if vectors A which is 1, 2, 3, and B, which is 4, 5, 6, if these two vectors form adjacent sides of a parallelogram, okay, the area of the parallelogram, is given by the magnitude of their cross products, the magnitude of their cross products. Okay, so we already know how cross products go. We have to form a matrix, and all of that will go. Magnitude of their cross products. Okay. I'm trying to put everything together properly. Yeah, we know the idea of cross products normally. Okay, so let's go. So we have A cross B, right? And we know A cross B is just simply the magnitude of I, J, more like the determinant, right? Determinant of ijk. And the first vector A is 1, 2, 3. And then we have the second vector B, which is 4, 5, 6. So all we just need to do is to put all this together. So we find the determinant of this, which is, so I'll just go straight since we've done this before. So if you want to understand how this works, you can check set operations. You can check set operations. That will clarify the point here. So here we just have I, that's plus I, into, okay, maybe I can still demonstrate a bit. So you have, so because you're focusing on I now, that's plus I, cross the row, column, cross the row. So you have 2 times 3. 2 times 3, you have, 2 times 6, 12, minus 3 times 5, that's 15. Then once that is done, then take away this. And then the next thing is minus j into, so cross out the column and the row for j. So 1 times 6, that is 6, minus 3 times 4, that is 12. Then again, take that away. And now the focus goes to k. So the focus goes to k, so that we have plus k. So don't forget we have plus, minus, plus, and I explained that previously in a video before now. So if the focus is now on k, so cross out the column, cross out the row. So we have 1 times 5, 5, minus 4 times 2, 8. So that this is now 12 minus 15 is minus 3. So we have minus 3i. Then 6 minus 12 is minus 6. So minus 6 times minus 8, that is plus 6j. Then lastly, 5 minus 8 is minus 3. So we have minus 3k. So this is the cross product of this vector. So that is the cross product of this vector. So of course, the area of the parallelogram is the determinant of the cross product. So now we have to still find the determinant of that cross product. So we can say, therefore, the area of the parallelogram, is the determinant of A cross B. So that means we are looking for the determinant of, minus 3i plus 6j minus 3k. And we know how that goes. So we take square roots of the sum of the squares of the components, and then we evaluate and we get our results. So I'll get to that in just a moment. Okay, so this is equal to square root of minus 3 squared plus 6 squared plus minus 3 squared. So that this is square root of 9 plus 36 plus 9. 9 plus 36 is 45. 45 plus 9 is 54. So that is root 54 for that. So it's equal to square root of 54. And of course, that is approximately 7.35. 7.35. Well, it is area, right? That is square units. 7.35 square units, something like that. So that brings us to the end of the application of vectors to geometry. Now let's talk about physics, which is the second part of this. Applications of vectors in physics. Okay, we consider 3 parts here. So we're also going to see 3 applications in physics. So applications of vectors in physics. Right. So let's say the first application will be about force and motion. So if a force F is applied to a mass M, it results in an acceleration. This is actually I mean, talking about kinematics now. It results in an, okay, in fact, is it even kinematics? I think it is dynamics, because kinematics is motion without caring about the force causing it. But dynamics is motion and the force causing it. So since you're talking about force, then it has to be dynamic. So it results in an acceleration vector A. So given by Newton's second law. Because the force is in the same direction with the acceleration and it is proportional to it. So the Newton's second law is F equals M times acceleration. So that's what that is. So what's the application? Vectors are used to represent forces, acting on objects. Forces acting on objects. The resulting accelerations. So vectors can be used to represent forces acting on objects. The resulting accelerations from those movements, and even velocities. So you can use vectors to represent force, acceleration, and velocities. That's simply what that is about. So for instance, in projectile motion, that's you launching an object from an angle above the ground. So for instance, in projectile motion, the velocity vector can be decomposed into horizontal and vertical components. So, I mean, we've seen the composition of vectors. I think in the previous video where we looked at vector components, we have seen how that could be done. So, can be decomposed into horizontal and vertical components to analyze the trajectory of the object. Okay. So, having spoken that much English, let's do a simple example and get it moving. So, let's take this example. A 10 Newton force F, which is given as 10, 0 this way, is applied to a 2 kg object. Okay. So the resulting acceleration, since we already have a formula for that, the resulting acceleration would simply be, normally we have F is equal to M times acceleration. So that would mean that acceleration itself, which you're looking for, is actually divided both sides by the mass. So that's the force divided by mass. Of course, mass is a scalar, while acceleration and force are vectors. So in this case, we simply have the acceleration to be equal to the force. The force is 10, 0, and the mass is 2 kg. So we have divided by 2 down here. So that simply means we have the acceleration to be 1/2 times 10, 0. So that's more like saying acceleration is 10 times half, then 0 times half, like that. So that 10 times half is 5, and 0 times half is simply 0. So the acceleration is actually the acceleration is just 50 meter per squared second. That's the acceleration that happens in that object. So if we now have, if another force, F2, which is 0.5 Newton, is applied simultaneously, the total acceleration, so you know the force has increased, so it is going to cause a faster motion, so to speak. So the total acceleration would be A total, that's total acceleration, which is of course the first acceleration, that is 10-0, plus the second acceleration. Okay, let me even write that as a formula first. So this is, so previously we had just F, so that'll be the initial force plus the second force, F2 now, okay, divided by the mass of the object. So it's still the same object. So that means that the total acceleration, A total, will be 10-0 for the first force plus 0.5 for the second force. So we can add component by component, and we are dividing by 2 kilograms. So A total here now is 10.5 divided by 2, which again is A total acceleration, that is half of 10.5. So that means that A total is 10 times half, 5 times half. So that means the acceleration, finally, A total, will be equal to 5.5, then 2.5 meter per squared second. So that means it is accelerating at 5 meter per squared second in the x-axis, and it is accelerating 2.5 meter per squared second in the y-axis, because this has two components now. So that's a very good example of application of vector in physics. That's talking about force and motion. That's the first application we have seen. That's force and motion. So let's see the second application of vector in physics. So the second one will be about work done by a force. Work done by a force. So work done by a force. So work done by a force. The work done by a force F moving, an object along a displacement, D is given by W equals force dot D. That's the dot product of force and the displacement. You know, work done is force moved over a distance or something like that. And that's why the formula is work done is the dot product of force and the displacement. And talking about the application, right? In physics, work done by a force is calculated using the dot product. It's using the dot product of the force because the work done at the end of the day is going to be a unit, is going to be a scalar. That's why, and the only way you can get a scalar from two vectors is by taking their dot product. So using the dot product of the force and displacement vectors So this concept is crucial. This concept is crucial in understanding in understanding energy transfer, energy transfer in mechanical systems, in mechanical systems. So that's talking about work done by a force. So let's take an example of that. So example, a force F, which is 7.3 Newton. That's 7 in the X direction and 3 in the Y direction. So this force moves an object along a displacement, D, which is 24 meters. So the work done is W, which is force dot distance. So work done is dot product of force and displacement rather. So that means we have W to be 7324. That's 73.24. So since it is dot product, I and I work together, J and J work together. So you have 7 times 2 plus 3 times 4. So, and work done now would be 7 times 2 is 14, 3 plus 4 is 12. So work done is 26. That's 26 joule. That's the unit of measure for measuring work done, joules. So because at the end of the day, we just need it in joules. That's why we use dot products, because it's a scalar quantity. Okay, so we have 2 more applications under physics. So the third one is what you call torque. Torque. 3, Torque. Torque. So torque, which is tau, that's a vector tau, produced by a force F, acting at a distance, R from a pivot point, is given by so tau, which is the torque, equals the distance R, the cross product of the distance R and the force itself. So here we have cross product coming into it. So, and the application is like this. So torque is a vector quantity. So you see, work is a scalar quantity while torque is a vector quantity. So because work is scalar, that's why we have to do dot product. And because torque is a vector, we have to do cross product. So torque is a vector quantity. Torque is a vector quantity that describes the rotational effect of a force applied at a distance from a pivot. So you apply a force to something and then it makes the object rotate. So from a pivot. So it is fundamental in analyzing the rotational dynamics of objects, and analyzing the rotational dynamics of objects. So that's talking about torque. And we know it's important we know what is scalar, what is vector, so we can know how to go about handling them. Okay, so here we're talking about torque. So example, a force F which is 4.3 Newton. That's 4 Newton in the horizontal direction and 3 Newton in the vertical direction. A force F 4.3 is applied at a point R, which is 2.1 meter from a pivot. The torque is tau, which is R cross F. So here we just have R is 2.1. R is 2.1 cross F, which is 4.3. Well, we are talking about cross product, so we can be doing, so we have to do, I think we need at least 3 components. So let's make it this way. Let this be 143 and let this be 0 to 1. Okay, 143 and 0 to 1. So 0 to 1, 143. That's we need the cross product of that. So that means the torque itself is the determinant of I, J, K. Then we have 0 to 1, and then we have 143. And then we do the same thing. So this is the torque now will be K. That's the same thing we did before. So if you take I, that's positive I, into cross the column, cross the row. 2 times 3 is 6, minus 4 times 1, that's 4. 4 times 1, that is 4. Then the next thing is we go to J, which carries a negative sign now. So we go to J. So this is positive, this is negative, this is positive. So negative J into, then cross the column, cross the row. So 0 times 3, that's 0, minus 1 times 1, that's 1. Then lastly, we go for K, which carries a positive sign. So in that case, cross the column, cross the row. 4 times 0 again, that's plus K now, into 4 times 0, 0. 2 times 1 is 2. So putting it all together, we have torque to be I into 6 minus 4, 2, minus J into 0 minus 1, minus 1, plus K into 0 minus 2, that's minus 2. And we put it all together. So the torque is simply 2I plus J. That's 2I plus J, 2I plus J minus 2K. So that is the torque. So in case you now need the magnitude of the torque, you can deal with that. So let's take the last application, which is something about magnetic fields. So the fourth application, so here we are taking 4 applications. So the fourth and last application, of course, there are many more applications, but this is the last that we're talking about in this case. Okay. So 4, we have electric and magnetic fields. Electric and magnetic field. So you can see how vector can be really useful in all these areas. Electric and magnetic fields. So the force F on a charge Q, Q, moving with velocity V in a magnetic field B is given by the Lorentz force equation, which is F equals the charge times the velocity multiplied by the magnetic field, like that. So what's the application of that? So vectors are essential. in electromagnetism, okay? Electromagnetism, to describe electric and magnetic fields, electric and magnetic fields. Electric and magnetic fields, forces that are on charges, forces on charges, and the directions of induced currents, So the right-hand rule is often used to determine the direction of the magnetic force, of the magnetic force on a moving charge, Okay, so let's take the practical example on that. So with that, we almost come to an end. So quickly, we have this example, a charge Q, as you can see, a charge Q, which is 2C, I don't know. What is it? I think it's 2 coulomb. Charges are measured in coulombs or something, I'm not sure. So a charge Q, which is 2 coulombs or so, moves with, and of course, a charge is a scalar quantity, as you can see, moves with velocity, V, which is given by 340 meter per second in a magnetic field, B, which is 0.05. So I think that's measured in Tesla also. So the magnetic force on the charge, okay, I guess I should start that fresh to show that that's us going for the calculation. So the magnetic force on the charge is F, from the formula we had previously. F, that is, as vectors go, right? This is Q V cross B. So, I mean, Q is a scalar quantity, so it can stand outside. So you have Q, then V cross B, like this. So normally that should be F equals, so Q itself, right? Q is 2 coulombs or so. Then multiplied by the determinant. So we have I, J, K. And then what is V? V is 340. So this is 340, and this is 0.05. Okay, so that F itself is equal to 2 times. So now let's do the whole determinant thing again. So we have done that we have done that a couple of times, so it should be easy. So we have I, of course, plus goes with that. So cross this and cross that. So that will be 4 times 5, that's 20, minus 0, that's 20. Then then focus on J now. J has a minus. So cross the column. Cross the row, cross the column. 3 times 5 is 15. So that's minus J into 3 times 5, 15 minus 0, that's 15. Then lastly, we focus on K. So focus on K. Cross the column, cross the row. 3 times 0 is 0. So that's plus K into 3 times 0 is 0. 4 times 0 is also 0. So 0 times 0 is 0. So that K part will be gone. So that if we tidy up all this, so the force, I think the force on the charge, which we have calculated, the magnetic force on the charge is now going to be 2 multiplied by 20I minus 15J Of course, this crosses out because the Z part is gone. So finally, we have F to be 40I minus 15J. So the magnetic force on the charge can simply be said to be 40 minus 15. Okay, well, I guess I should still put it there, right? Okay, I think it's proper I just put it since we started with 3 components. So the one component cannot just disappear. So the worst it can be is 0. So we just have plus 0k. Okay, I think that helps. So this is plus. So 2 times that is still 0k. So we have 40 minus 15. Oh, okay, I did not do that properly. So 40, 2 times minus 15, that's minus 30. So 40 minus 30 is 0. So 40 minus 30, 0. Yeah, this has been such a long journey. So if you have not subscribed to this channel, be sure to do that because you have a whole lot to learn. And after subscribing, be sure to hit the notification bell so you can always get alerted when a new video is released. Then comment, like, and share so that more and more people can have access to this. So of course, the force on the chart, like we said here, is actually 40 Newton in the X direction, 30 Newton in the Y direction, and 0 in the Z direction. So see you next time.